Now, in the coming videos, we're going to learn a lot more about the individual components of the solar system in greater detail. But now that we understand how the solar system formed, let's just take a quick look around and see what's out here. Our solar system consists of one star, the Sun, and then we have a few relatively small rocky planets. These are the terrestrial planets, Mercury, Venus, Earth, and Mars. And for the purposes of our discussion, we'll include the Moon as well, even though it's not really a planet. And then we have a giant belt of asteroids. These are tiny little rocks, or comparatively speaking, tiny rocks, that number up to about 1 or maybe 2 million. We don't really know exactly how many asteroids there are out there. We keep discovering them literally every day. Following the asteroid belt, we have the giant planets, and we further subdivide the giants into two forms. There are the gas giants, that is Jupiter and Saturn, followed by the ice giants. So later on, we're going to talk more about these worlds. But the ice giants are really composed of mostly methane and ammonia ices. So there are as much water worlds as they are gas worlds, with a lot of ice in between. Finally, in the outer reaches of the solar system is something called the Kuiper Belt. You can think of the Kuiper Belt as a kind of like a second asteroid belt, except that these objects are, number one, much farther from the Sun, and number two, are mostly composed of ices and other volatile elements, whereas the asteroids are mostly composed of refractory materials. Now, inside the Kuiper Belt, there are some really large objects. They're so large that they've actually pulled themselves into a round shape, and we call these the dwarf planets: Pluto, Charon, Eris, Makemake, Haumea. And because it is round and because it orbits the Sun, Ceres in the asteroid belt. When we think about all of the stuff in the solar system, it's dominated by the Sun. In other words, the Sun occupies 99.8% of the mass of the entire solar system. Everything else is in that remaining 0.2%. And of that remaining 0.2% of the mass, Jupiter takes half of that. So Jupiter's at 0.1% of the mass, and that means Earth, the planets, the Moon, all the rest of the asteroids, comets, you name it, all falls into that last 0.1% of the mass of the solar system. And solar system objects all have several characteristics that they have in common, with notable exceptions. So let's go through some of these. First of all, they all orbit the Sun, except of course for the moons and the rings, which orbit other planets. They all rotate on their axes in the same direction, except for Venus, Uranus, Pluto, and probably some other things. And everything in the solar system orbits the Sun in the same direction. In other words, if you could imagine yourself above the solar system, you would look down and see everything moving in a counterclockwise direction. But occasionally there's a comet or two that will come in a clockwise fashion. And everything tends to orbit the Sun in roughly the same plane. In other words, if you think of the solar system as seen edge on, everything would kind of line up going from the Sun out to Neptune. But once you get past Neptune into the Kuiper Belt, things start to be a lot more inclined. We see objects sometimes having orbits as high as 40 or 50 degrees inclined with respect to the rest of the planets in our solar system. And everything is made of more or less the same stuff. The primary difference is in different quantities or ratios. Some have more rocks and little volatiles. Others are mostly volatiles and have very little rock. And some are rock only and others are volatile only. Everything in the solar system rotates on its axis. The Earth has a rotational axis that's tilted from the direction of its orbit by about 23.5 degrees. And Mars and Saturn and Neptune all have very roughly similar axial tilts. However, when you look at Mercury and Jupiter, they have virtually no axial tilt. Now remember, the axial tilt is the reason for the seasons, right? So the fact that Mercury and Jupiter really don't have any axial tilts to speak of, in other words, they're pretty much rotating perpendicular to the directions of their orbits, that means that these two planets really don't experience any seasonal variations. Mars and Saturn and Neptune have seasonal variations that are at least similar in principle to Earth's seasonal variations. However, when you look at Uranus and Pluto, they are basically rotating on their sides. So these two worlds would have the most extreme seasonal variations of any worlds in the solar system. Now, a real strange duck is Venus. Its axial tilt is basically 180 degrees. In other words, it's been knocked over. So the planet is really rotating backwards, and we call this a retrograde rotation. And it's not exactly clear why this happened, but the best explanation is that Venus was probably knocked into or knocked over by some previous planetesimal back in the early days of the solar system. So everything rotates on its axis, but when we look at the planets themselves, now we can start thinking about them in terms of their compositions. So let's start with the giant planets. As we talked about before, there are gas giants and ice giants, and what do they all have in common and what's different? Well, first of all, they're all more massive than Earth, right? There's not only are they larger, but they are simply more massive. There's more planet there. Jupiter is nearly 318 times the mass of Earth, and Uranus is a relatively puny 14 times the mass of Earth. So everything's a lot more massive. And of course, they're much larger, right? So you take Jupiter, and it has a diameter of about 11 Earths. Again, Neptune is kind of quaint at just 4 Earths in diameter. And the densities of these planets are really, really low. And that's because of what they're made of. They're all made of these lightweight, volatile materials. We're talking about things like hydrogen and helium and ammonia ices and methanes and so forth. I mean, that's really lightweight, low density stuff. So it's not surprising that these planets have low densities. Now, these densities are presented as ratios to Earth, but it turns out that the absolute bulk density of Saturn is less than 1 gram per cubic centimeter. In other words, Saturn would float in water if you could find a bathtub large enough to accommodate it. Now, these planets, being that they are made of gas, do not have any surfaces you can walk around on. There is no picking up a rock on Jupiter or throwing a snowball on Neptune. It doesn't work that way. They're gas and ultimately liquid all the way down to their cores. So you can't really walk anywhere. But if you could imagine yourself floating in the atmosphere of these planets, let's say you're inside some kind of a dirigible floating in the atmospheres, the upper atmospheres of these planets, well, then you could weigh something. And if you stood on a scale, you would find that on Jupiter, you weigh about 2.3 or 2.4 times your weight on Earth. But if you are on Saturn, you pretty much weigh what you already weigh on Earth, maybe even a little bit less. Now, why is it that you would find yourself weighing less on some of these planets? After all, aren't these planets more massive than Earth? Well, yeah, they are. Absolutely. There's no question about that. But you got to remember how gravity works. It's a combination of your mass, the planet's mass, and it's the inverse of the distance between you and the center of the planet squared. So because these planets are so large, they have low or relatively low surface gravities. Now, the rotational periods of these planets are really short, and that means that they're rotating very quickly. You might think that they should rotate very slowly. After all, they are really, really big. But the fact is that they have a great deal of mass brought into a relatively small volume, at least small by the standards of the solar system. That means that they have a lot of angular momentum, and therefore they have to rotate very rapidly in order to keep the angular momentum conserved. So they're going to have short rotational periods or short days. Now, the gas giants are different from the ice giants in their composition. Gas giants are mostly composed of molecular hydrogen and metallic hydrogen. When it comes to the ice giants, on the other hand, well, this is why we call them ice. You do have hydrogen, helium, and methane in the upper layers, but its interior mantle is mostly going to be water and ammonia and methane ices. So the interiors of these planets are slushy. Let's talk now about the terrestrial planets. And again, we're going to include the moon in this discussion. So we're going to compare everything to Earth once again, and we find that the masses of all these planets are a little bit less than Earth. Venus is the closest in terms of mass. The sizes are also smaller than Earth, although Venus is essentially Earth's twin in this regard. Likewise, the bulk densities of these planets, well, there's some surprises here. The Moon and Mars both have a lower density overall, as we would expect. But you notice that Mercury, and not Venus, is the next densest object in the solar system. And this has a lot to do with Mercury's formation, as we're going to learn about later. But basically, we think that Mercury once upon a time was on its way to becoming a Venus or Earth-sized planet, and something stripped off its outer layers, leaving behind a core and a relatively thin mantle and crust. So this is why Mercury has such a high density. The gravity on the surface of these worlds varies a little bit. Venus is unsurprisingly very similar to Earth. So you would weigh about what you weigh on the surface of Venus, as you do here on Earth. But when you're on Mars, you suddenly have lost some weight, as you have lost quite a lot of weight on the Moon. Now, the rotational periods of these planets are a little bit different. Mars and Earth both have very similar rotation periods. Mars's rotation period is just a little bit longer than Earth's. However, Mercury and Venus both have much longer rotations, and this is for very different reasons. We think Mercury has a long rotation period because of tidal interactions between the Sun and the planets outside of its orbit, whereas Venus probably would have had a more Earth-like rotational period, but something interfered with it, knocking it over, causing it to reverse its rotational direction, and as a result, losing a lot of energy in the process, so it has a very long rotation. As a matter of fact, a day on Venus, if you think about rotating once on its axis, is actually longer than a year on Venus. Now, the thing that really differentiates these planets from everything else in the solar system is that they are differentiated. In other words, what we're saying is that when all these planets were forming, there were all kinds of materials flying around everywhere. We learned about how planetesimals grow and they collide with other planetesimals. They break apart and they melt and they form together again. So when these smash together, they're very hot and they liquefy. They melt. So these planets were once molten. And that allowed all of the dense materials, the nickels, the irons, and so forth, to sink into their cores, while their surfaces and mantles would be composed of mostly rocky silicates. So you have these planets with mostly 2/3 rocky silicates, mostly in the mantle and in the crust. And then you've got these iron, nickel, and iron sulfur cores, the really dense stuff that sinks into the very core of the planets. So everything we've talked about so far is what we now refer to as a classical planet. These planets all orbit the sun. They all have roughly the same plane, and they've all cleared out their orbits. However, we have a number of objects way beyond the orbit of Neptune, and for this reason we call them trans-Neptunian objects, or TNOs. So these are all illustrations with the exception of Pluto. Those images of Pluto and Charon are made possible by the New Horizons spacecraft, which flew past those two worlds in 2015. Everything else is an illustration. Here are some actual images of these objects. So Pluto, Eris, Makemake, and Haumea, and Ceres are classified as dwarf planets. Okay, so why are they dwarf planets? This was a decision that was made back in 2006. And it seemed to get people kind of upset because they thought that Pluto was no longer considered a planet. In fact, Pluto is still a planet, but it's a dwarf planet. So what is a dwarf planet? Well, a dwarf planet is an object that orbits the sun, just like Earth and Jupiter and so on. These planets are massive enough that they were able to pull themselves into a round shape and achieve hydrostatic equilibrium. However, unlike the so-called classical planets, these planets have not cleared out their orbits. We saw earlier, as planets were forming in the simulations, how they were sweeping out their orbits. Well, these planets have not. In fact, they share their orbits with other objects, other TNOs. So that's why we distinguish dwarf planets from classical planets. And you may be thinking, well, Haumea is believed to be a oblong shape. What's going on there? Well, the idea is that Haumea has a very, very short rotation period. So the estimation is that it's probably stretched itself into this oblong shape, so it's otherwise round. Now, we have a lot of other stuff that are not planets in the solar system, and let's just take a quick look at some of these. First of all, there are asteroids. We have on the right-hand side, you have some asteroids from the asteroid belt, and you notice that on the left side, we have 2 moons of Mars, which we think may be captured asteroids. So they probably started out somewhere in the asteroid belt and were pulled into an orbit around Mars, perhaps. The asteroids themselves are planetesimals, and they're just leftovers from the early construction of the solar system. Most asteroids are not differentiated. Some are, but most of them are not. In other words, they never got molten or they never had a chance to get that hot in the first place. And we often categorize them by their composition. So we have the C-type, which is carbonaceous in nature, the stony types, and even the metallic types. It's probable that the metallic types were probably once molten cores of protoplanets that got smashed apart. Moons are anything that orbit planets instead of the sun. And if you go out into the outer solar system, you will find that every major planet out there is chock-a-block with moons. One of the cool things about these moons is that they're all similar in composition to the interiors of the planets. And it turns out that they all seem to have differentiated interiors, which tells us something about their formation history. So they're going to have rocky, metallic cores with water and ice crusts. The exception being Jupiter's moon Io. That's really a volcanic world, so any water and ice would have long since evaporated. There are many different types of moons, but they basically come in 2 major flavors. The first are regular moons, so those are the types of moons that we just talked about. They formed with their planet. But there are also a lot of irregular moons that are basically captured asteroids. They formed elsewhere, and they were just captured into an orbit around Jupiter. Finally, we have comets. These are the dirty snowballs, and best of all, they are the most pristine objects in our solar system. Comets, therefore, are going to be undifferentiated, and because they are really just chunks of volatiles, they're dirty chunks of volatiles, they will outgas once they're heated. So as they come a little bit closer to the sun, they produce these characteristic tails. Now, when we think about the temperatures on the surfaces of these planets, obviously, the closer you are to the sun, the hotter your surface temperature should be. This is what we expect to see, right? However, when we measure the surface temperatures, we get a different result. And that's because it's more than just the distance from the sun that determines the surface temperature. There's also something called albedo, and that's a measure of how reflective a planet's surface is. So if a planet reflects most of the light, then it has a high albedo, and therefore it's going to stay relatively cool. But if the planet is really dark, then it's going to absorb more light and warm up. And remember, most of these planets have atmospheres, namely Earth. So there's a greenhouse effect, which further raises temperatures at the surface. And finally, planets have varying degrees of internal heat. At least some do. Others, like Mercury and Mars, probably no longer have much internal heat at all. But planets like Venus, Earth, Jupiter, Saturn, Uranus, Neptune, all of these worlds have internal heat, which occasionally manifests itself near their surfaces. We have things like volcanoes and other activities that keep the surface warm from within. So that's a very quick look at our solar system. And from here on out, we're going to explore different categories of worlds in greater detail.